Hello there, and welcome to the Sleepy Astronaut, where distant worlds whisper their secrets and cosmic mysteries unfold like gentle dreams. Tonight's extraordinary journey takes us 48 light years from home to meet a planet that has turned everything we thought we knew about worlds beyond our solar system completely upside down. This is the story of Enaiposha, a world so peculiar, so utterly confounding, that it has forced astronomers to rewrite the textbooks and question the very foundations of planetary science. Before we venture into the depths of space to explore this enigmatic world, I'd love to know where in the universe are you joining me from tonight and what draws you to the mysteries that lie beyond our pale blue dot. Fitting, isn't it? A video about a world that defies classification, and here we are scattered across our own world, each of us gazing up at the same stars, wondering what secrets they hold. If you find this cosmic voyage soothing, intriguing, or simply a peaceful way to drift into dreams, I'd be ever so grateful if you gave the video a like and perhaps subscribed it. Helps this little corner of astronomical wonder reach other stargazers who might need a moment of celestial calm. Now, I do hope this tale of distant worlds isn't so captivating that it keeps you from your rest, but if it does, well, at least you'll have journeyed to another planet before closing your eyes. So settle in, let your imagination soar, and let's begin. Because somewhere in the constellation, Ophiuchus, orbiting a dim red star, lies a world that challenges everything we thought we understood about the cosmos. Enaiposha doesn't look like much at first glance, just another dot of light transiting across its parent star. But this unassuming world, officially designated GJ12b, has become one of the most important discoveries in modern astronomy. A planet that sits in that mysterious realm between Earth and Neptune, a size category that simply doesn't exist in our own solar system, yet represents the most common type of planet in the entire galaxy. The name Enaiposha itself tells a story in the Ma language. It means large body of water, a designation that seemed perfectly fitting when astronomers first discovered this world. In 2009, they envisioned a water world wrapped in thick clouds of steam, an ocean planet unlike anything in our cosmic neighbourhood. But sometimes the universe has a sense of humour, and Enaiposha, as we've come to understand it, is nothing like what scientists initially imagined. When the Kepler Space Telescope first began its planet-hunting mission, astronomers made a startling discovery: more than half of all sun-like stars in our galaxy host planets that are completely absent from our own solar system. Worlds larger than Earth but smaller than Neptune. These sub-Neptunes, or mini-Neptunes as they're sometimes called, orbit. They're stars closer than Mercury orbits our Sun. Yet they represent the most populous planetary family we've ever encountered. This discovery was profound and deeply unsettling if such planets are so common throughout the galaxy. Why don't we have any in our own solar system? What does this say about how typical or atypical our cosmic home truly is? It's as if we'd been studying architecture our entire lives using only the buildings in our own neighbourhood, only to discover that most of the world lives in structures we'd never even imagined. Enaiposha belongs to this mysterious category of worlds, and for over a decade it has been the white whale of exoplanet research, a planet so shrouded in mystery, so wrapped in impenetrable atmospheric haze that it defied every attempt to understand its true nature, previous telescopes including the mighty Hubble Space Telescope could peer at this world, but they could never quite penetrate the veil that surrounded it. Imagine trying to understand a person by looking at them through frosted glass. You can see that someone is there, you can make out rough shapes and movements, but the details, the crucial information that would help you understand who they really are, remains frustratingly out of reach. That's exactly the challenge Enaiposha presented to astronomers for more than a decade. The planet orbits its red dwarf star, GJ1214 every 1.6. Earth days locked in a perpetual dance where one side forever faces the star in endless day, while the other side stares out into space in eternal night. This tidally locked configuration creates extreme temperature differences and atmospheric dynamics unlike anything we see on planets in our own solar system. But it was the atmosphere itself that proved most puzzling. Early observations revealed the presence of a thick, hazy envelope surrounding the planet. But what was this haze made of water vapour? Methane, hydrogen, helium, or something else entirely? The traditional tools of astronomy could only provide tantalising hints, never definitive answers. Then came the James Webb Space Telescope, humanity's most powerful eye on the cosmos, equipped with instruments so sensitive they can detect the faintest whispers of light from the most distant corners of the universe. When JWST turned its gaze toward Enaiposha, everything changed in ways that no one quite expected. Using the telescope's mid-infrared instrument, astronomers embarked on an unprecedented observational campaign. They didn't just watch Enaiposha transit across its star, they tracked it through its entire orbit, creating the first complete thermal map of a sub-Neptune exoplanet. What they discovered was nothing short of revolutionary. The thick haze that had frustrated astronomers for so long began to reveal its secrets. Beneath those impenetrable clouds lay an atmosphere unlike anything previously discovered. The planet's upper layers are filled with aerosols and complex molecules, creating a barrier so reflective that it bounces back much of the starlight that hits it, rather than absorbing it, and heating up this discovery alone was remarkable. But it was just the beginning, as the data poured in from JWST. Astronomers realized they were looking at something that challenged the very categories they used to classify planets. Enaiposha wasn't quite the water world they'd imagined, nor was it a typical mini-Neptune. Instead, it appeared to be something entirely new. The breakthrough came when scientists detected carbon dioxide in the planet's atmosphere. Not just trace amounts, but concentrations comparable to what we find in the dense carbon dioxide atmosphere of Venus in our own solar system. Suddenly, the picture began to shift. This wasn't a mini-Neptune at all. It was something that had never been seen before, a super-Venus. The implications were staggering. If Enaiposha represents a new type of planet, then our understanding of how worlds form and evolve needs to be completely reconsidered. The presence of carbon dioxide in such quantities suggests atmospheric processes and evolutionary pathways that existing theories struggle to explain. But the mysteries don't end there. The temperature variations across Enaiposha's surface tell their own fascinating story. The day side, where the red dwarf star beats down relentlessly, reaches temperatures of 535 degrees Fahrenheit, hot enough to melt lead. Meanwhile, the night side perpetually turned away from the star drops to a relatively cool 326 degrees Fahrenheit. This temperature difference reveals something crucial about the planet's atmospheric circulation. The atmosphere is surprisingly poor at transporting heat from the scorching day side to the frigid night side, creating a world of extreme contrasts that challenges our understanding of atmospheric dynamics. The chemical composition of Enaiposha's atmosphere provides even more puzzles, alongside the carbon dioxide. Astronomers have detected water vapour and methane gases that on Earth are often associated with biological and geological processes. While Enaiposha is far too hot to support life as we know it, the presence of these molecules raises intriguing questions about the chemical processes occurring in its extreme environment. Perhaps most importantly, the discovery of heavy elements in Enaiposha's atmosphere suggests that this world has retained or accumulated materials that should have been stripped away by stellar radiation over billions of years. This finding challenges our understanding of atmospheric evolution and raises questions about how planets in close orbits around their stars can maintain such complex atmospheric compositions. The story of Enaiposha is still being written, with each new observation revealing additional layers of complexity and mystery. This world that once seemed like a simple water planet has transformed into a cosmic laboratory where the fundamental processes of planetary formation and evolution play out in ways we never anticipated. As we continue our journey through the cosmos, exploring the secrets of this remarkable world, we'll delve deeper into the revolutionary observations that have redefined our understanding of planetary science. We'll examine how the James Webb Space Telescope pierced through Enaiposha's mysterious haze, and what those discoveries mean for our search for other worlds throughout the galaxy. The universe, it seems, has many more surprises in store for us, And Enaiposha is just the beginning of a new chapter in our understanding of the incredible diversity of worlds that exist beyond our own solar system. So let us continue this cosmic voyage together as we unravel the mysteries of a planet that has forever changed how we see our place in the universe. The revelation that Enaiposha might be a super Venus, rather than the water world scientists originally envisioned, represents one of the most dramatic paradigm shifts in modern planetary science. It's rather like expecting to meet a gentle librarian and instead encountering a fire-breathing dragon. Both are fascinating in their own right, but they require entirely different approaches to understand. This reclassification didn't happen overnight or through a single eureka moment. Instead, it emerged through painstaking analysis of data so subtle that detecting it was like trying to hear a whisper in a thunderstorm. The signals were there, buried in the infrared light streaming from this distant world, but they required the most sophisticated instruments humanity has ever built to tease them from the cosmic noise. The James Webb Space Telescope's observations revealed something extraordinary about Enaiposha's atmospheric composition. The carbon dioxide detected in its atmosphere exists in concentrations that rival those found in Venus's crushing greenhouse environment. On Venus, carbon dioxide creates surface pressures 90 times greater than Earth's and temperatures hot enough to melt zinc. While Enaiposha's atmospheric pressure remains unknown, the presence of substantial carbon dioxide suggests processes at work that could create similarly extreme conditions. But carbon dioxide wasn't the only surprise lurking in Enaiposha's atmospheric cocktail. The detection of water vapor and methane alongside the carbon dioxide creates a chemical puzzle that has atmospheric scientists scratching their heads. On Earth, these three gases tell stories of geological activity, biological processes, and climate dynamics. On a world orbiting so close to its star that it completes an orbit in less than 2 days, their presence suggests atmospheric chemistry operating under conditions we can barely imagine. The methane detection is particularly intriguing because methane is notoriously unstable in the presence of ultraviolet radiation from a star. Under normal circumstances, stellar radiation should break down methane molecules relatively quickly. Yet there it is persisting in Enaiposha's atmosphere, which suggests either continuous replenishment through unknown processes or atmospheric conditions that protect it from destruction in ways we don't yet understand. The thick haze that shrouds Enaiposha adds another layer of mystery to this already complex world. This isn't simply water vapor or ice crystals like the clouds we see on Earth or even the sulfuric acid clouds that blanket Venus. The haze appears to be composed of complex organic molecules, possibly similar to the tholins found on Saturn's moon Titan, but existing under entirely different temperature and pressure conditions. These organic compounds, if that's indeed what they are, could form through photochemical processes in the upper atmosphere, where stellar radiation breaks down simpler molecules and allows them to recombine into more complex structures. It's rather like a vast atmospheric chemistry laboratory operating continuously above the planet's surface, creating compounds that may not exist anywhere else in the solar system. The reflective properties of this haze have profound implications for Enaiposha's energy balance. By bouncing back much of the incoming stellar radiation, the haze acts like a cosmic mirror, preventing the planet from absorbing as much energy as it would otherwise. This creates a feedback loop where the very processes that create the haze also help regulate the planet's temperature in ways that traditional climate models struggle to predict. The temperature measurements from JWST reveal another fascinating aspect of Enaiposha's character. The stark contrast between day and night temperatures tells us that despite having an atmosphere, the planet is remarkably poor at redistributing heat. On Earth, our atmosphere acts like a great thermal blanket, spreading warmth from the sunny side to the shadowed regions. But Enaiposha's atmosphere seems to compartmentalize heat, leaving the night side hundreds of degrees cooler than the day side. This inefficient heat transport suggests that Enaiposha's atmospheric circulation patterns are fundamentally different from what we see on planets in our own solar system. Perhaps the thick haze inhibits atmospheric mixing, or maybe the atmospheric composition creates circulation patterns that trap heat on the day side, rather than allowing it to flow freely around the planet. The implications extend far beyond this single world, because if Enaiposha represents a new category of planet, then astronomers must reconsider how they classify the thousands of other sub-Neptune worlds discovered by planet hunting missions. Each of these distant worlds might harbour its own unique atmospheric chemistry and evolution story waiting to be uncovered by future observations. The discovery also raises profound questions about planetary formation and migration. How did a world with such a complex atmosphere end up orbiting so close to its star? Did Enaiposha form in the outer reaches of its solar system, where volatile compounds could condense and then migrate inward, carrying its atmospheric inventory with it? Or did it form closer to its star and somehow manage to retain or acquire its thick atmosphere despite the intense stellar radiation? These questions touch on some of the deepest mysteries in planetary science, because the formation and evolution of planetary atmospheres involves a delicate interplay between stellar radiation, gravitational forces, chemical processes, and timescales spanning billions of years. Understanding how Enaiposha acquired and maintained its unusual atmosphere could provide crucial insights into how planets throughout the galaxy develop their unique characteristics. The chemical inventory of Enaiposha's atmosphere also offers clues about the building blocks available in its stellar system. The presence of heavy elements suggests that when this planetary system formed, there was an abundance of materials beyond simple hydrogen and helium. This compositional richness might indicate that planets forming around red dwarf stars like GJ 1214 have access to a more diverse palette of chemicals than previously assumed. Red dwarf stars themselves present unique challenges and opportunities for planetary development. These stars burn their nuclear fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. This longevity means that planets orbiting red dwarfs have potentially vast amounts of time for atmospheric and surface evolution to occur. Enaiposha might represent just one snapshot in a multi-billion-year evolutionary journey that could continue for eons into the future. The habitability implications, while not directly applicable to Enaiposha itself, are nonetheless fascinating to consider. While this world is far too hot to support life as we know it, understanding how complex atmospheric chemistry develops and persists on planets orbiting close to their stars provides valuable insights for assessing the potential habitability of other worlds in the galaxy. The story of Enaiposha reminds us that the universe consistently surprises us with its creativity and complexity. Just when we think we understand the rules governing planetary formation and evolution, nature reveals new possibilities that challenge our assumptions and expand our understanding of what's possible in the cosmic arena. As we continue to study this remarkable world, each new observation adds another piece to a puzzle that seems to grow more intricate rather than simpler with time. The gentle red dwarf star, GJ 1214, and its mysterious companion have become a laboratory for understanding planetary processes that may be common throughout the galaxy, yet completely absent from our own solar system. The technological triumph that made Enaiposha's secrets accessible represents one of the most remarkable achievements in astronomical observation, a testament to human ingenuity and our relentless pursuit of cosmic knowledge. For over a decade, this world had been astronomy's most stubborn puzzle, a celestial sphinx that refused to yield its riddles to even our most sophisticated instruments. The challenge facing astronomers was rather like trying to read a book through several layers of thick gauze, while wearing sunglasses in a dimly lit room. Previous telescopes could detect Enaiposha's presence and measure basic properties like its size and orbital period, but the crucial details about its atmospheric composition remain tantalizingly out of reach. The Hubble Space Telescope, Spitzer Space Telescope, and ground-based observatories had all taken their turns peering at this enigmatic world, each returning with inconclusive results that only deepened the mystery. Then came the James Webb Space Telescope. humanity's most ambitious astronomical project, equipped with instruments so sensitive they could theoretically detect the heat signature of a bumblebee at the distance of the moon. When JWST turned its golden mirror toward Enaiposha, it employed a revolutionary approach that combined traditional transit observations with something far more sophisticated, a complete orbital phase curve that tracked the planet's thermal emission throughout its entire journey around its star. The mid-infrared instrument aboard JWST proved to be the key that finally unlocked Enaiposha's secrets. This remarkable device can detect infrared radiation at wavelengths where molecules like carbon dioxide, water vapor, and methane leave their distinctive fingerprints. But detecting these molecular signatures from a world 48 light-years away required data analysis techniques that pushed the boundaries of statistical science. The researchers, led by Everett Schlowin from the University of Arizona, describe the challenge in terms that capture both the complexity and the elegance of their achievement. Finding the subtle signals of atmospheric molecules in the flood of data was like searching for a single altered sentence in the entirety of Tolstoy's War and Peace. Every photon of light collected by the telescope carried information, but sorting the meaningful signals from the noise required computational techniques that would have been impossible just a decade ago. The breakthrough came through a combination of patience, precision, and innovative methodology. Rather than relying on a single observation, the team accumulated data over multiple transits and orbital phases, building up a statistical foundation robust enough to support their extraordinary claims. Each measurement was tiny, requiring careful analysis to distinguish real atmospheric signals from instrumental artifacts or stellar variability. Kazumasa Ono from the National Astronomical Observatory of Japan contributed sophisticated atmospheric modeling that helped interpret the observations. His computer simulations explored thousands of possible atmospheric scenarios, testing different chemical compositions, temperature profiles, and cloud structures against the observed data. Every scenario that successfully matched the observations pointed toward the same surprising conclusion: an atmosphere rich in heavy elements and dominated by processes unlike anything seen elsewhere. The precision required for these measurements boggles the mind. The temperature differences between Enaiposha's day and night sides amount to variations in infrared emission, so subtle that detecting them required the telescope to maintain extraordinary stability over many hours of continuous observation. Any drift in the instrument's calibration or unexpected variations in the star's brightness could have masked the planetary signals entirely. The observational campaign itself represented a masterpiece of astronomical coordination. As Enaiposha orbited its star, JWST tracked its thermal emission continuously, creating what amounts to a weather map of an entire alien world. When the planet passed behind its star, the telescope measured how much infrared light disappeared, revealing the temperature of the day side. When it emerged on the other side, the measurements captured the thermal glow from the night side. This orbital monitoring technique, while conceptually straightforward, required extraordinary precision in execution. The team had to account for variations in the star's own infrared output, calibrate the instrument's response across different wavelengths, and extract planetary signals that were often less than 1% of the total light detected. It's rather like trying to measure the warmth of a candle flame while standing next to a bonfire, requiring not just sensitive instruments but also clever observational strategies. The spectroscopic analysis that revealed Enaiposha's atmospheric composition pushed the boundaries of what's possible with current technology. Spectroscopy works by analyzing how molecules absorb light at specific wavelengths, creating distinctive patterns that serve as chemical fingerprints. But when these fingerprints are embedded in the faint infrared glow from a distant planet, extracting them requires computational techniques that border on the miraculous. The carbon dioxide detection in particular required extraordinary statistical care. The signal was so small that multiple independent analysis techniques were needed to confirm its reality. False positives in exoplanet spectroscopy can arise from instrumental effects, stellar contamination, or data processing artifacts, making confirmation of atmospheric detections a painstaking process that demands both technical expertise and scientific skepticism. The water vapor and methane detections presented their own unique challenges. These molecules have complex spectroscopic signatures that can overlap with other atmospheric components or be confused with instrumental features. Confirming their presence required not just detecting the right wavelengths, but also demonstrating that the observed patterns were consistent with realistic atmospheric models. Perhaps most remarkably, the observations revealed details about atmospheric circulation and heat transport that had never been measured for any exoplanet in this size range. The inefficient heat redistribution between day and night sides emerged from careful analysis of how the planet's thermal emission varied as different regions rotated into view. These measurements provide the first direct evidence for atmospheric dynamics on a sub-Neptune world, opening entirely new avenues for understanding how these common but mysterious planets work. The technical achievement represented by these observations extends far beyond a single planet. The methods developed for studying Enaiposha are now being applied to other worlds in this size range, gradually building a picture of atmospheric diversity among sub-Neptune planets. Each successful observation adds another data point to our understanding of how planets in this mass range can develop and maintain their atmospheric characteristics. The precision and sophistication of JWST's observations also demonstrate how far astronomical technology has advanced. The telescope's ability to characterize exoplanet atmospheres represents a capability that was barely imaginable when Enaiposha was first discovered. In just over a decade, we've progressed from detecting the existence of sub-Neptune planets to analyzing their atmospheric chemistry in detail. The success with Enaiposha has important implications for future exoplanet studies. The techniques pioneered in these observations will be refined and applied to other intriguing worlds, gradually building a comprehensive understanding of planetary diversity throughout the galaxy. Each new atmospheric characterization adds another piece to the puzzle of how planets form, evolve, and maintain their unique characteristics over billions of years. The collaborative nature of this achievement also deserves recognition. The discovery required expertise in observational astronomy, atmospheric modelling, data analysis, and theoretical planetary science. The team's success demonstrates how modern astronomy has become a deeply collaborative enterprise, bringing together specialists from around the world to tackle questions that no single researcher could answer alone. As we continue to push the boundaries of what's possible with current technology, Enaiposha serves as both an inspiration and a proof of concept. This world that once seemed impossibly mysterious has yielded its secrets to human ingenuity and technological prowess, reminding us that even the most challenging cosmic puzzles can eventually be solved with patience, precision, and the right tools. The story of Enaiposha's atmospheric revelations is still unfolding, with each new analysis of the JWST data potentially uncovering additional details about this remarkable world. Future observations may reveal seasonal variations, additional atmospheric components, or other dynamic processes that will further refine our understanding of this cosmic laboratory orbiting its distant red star. The profound implications of Enaiposha's discovery ripple outward through our understanding of planetary science like stones thrown into a still pond, each revelation creating new waves of questions that challenge the very foundations of how we categorize and comprehend worlds beyond our own. This single planet, orbiting its dim red star in the constellation Ophiuchus, has become a cosmic Rosetta Stone, helping astronomers decode the mysteries of an entire class of planets that represent the most common worlds in our galaxy, yet remain completely absent from our own solar system. The reclassification of Enaiposha from a potential water world to what scientists now call a supervenus represents more than just a change in terminology. It signals a fundamental shift in how we understand planetary evolution and atmospheric development. This transformation in our thinking mirrors the great paradigm shifts in scientific history, moments when new evidence forces us to abandon comfortable assumptions and embrace more complex truths about the universe around us. The concept of a super-Venus opens entirely new chapters in planetary science textbooks that haven't even been written yet. While Venus in our own solar system serves as a cautionary tale about runaway greenhouse effects and atmospheric evolution gone awry, Enaiposha suggests that Venus-like conditions might be far more common throughout the galaxy than previously imagined. The thick carbon dioxide atmosphere, the extreme temperatures, and the impenetrable haze all point toward atmospheric processes that could be replicated on countless worlds orbiting close to their parent stars. But Enaiposha isn't simply a larger version of Venus. It's something more complex and intriguing. The presence of water vapor and methane alongside the carbon dioxide creates an atmospheric cocktail that has no exact parallel in our solar system. This unique chemistry suggests that the pathways leading to Venus-like conditions might be more varied and nuanced than our theories currently accommodate, opening possibilities for atmospheric evolution that we're only beginning to explore. The discovery also raises fascinating questions about the relationship between planetary size and atmospheric retention. In our solar system, we see a clear progression from the thin atmosphere of Mars through Earth's temperate envelope to the crushing depths of Venus's carbon dioxide shroud. But Enaiposha, with its mass 8 times greater than Earth's, demonstrates that size alone doesn't determine atmospheric fate. The complex interplay between stellar radiation, planetary gravity, atmospheric chemistry, and time creates possibilities for atmospheric development that extend far beyond the simple models we've relied upon. The temporal aspects of Enaiposha's story add another layer of complexity to its scientific significance. This world has been orbiting its red dwarf star for billions of years, subjected to constant stellar radiation that should theoretically have stripped away any substantial atmosphere long ago. Yet there it remains, shrouded in its thick haze and maintaining its complex atmospheric chemistry despite the hostile environment. This persistence suggests that planetary atmospheres might be more resilient than we've assumed, or that there are processes at work that can replenish atmospheric components faster than stellar radiation can remove them. The chemical processes occurring in Enaiposha's atmosphere might serve as a natural laboratory for understanding prebiotic chemistry under extreme conditions. While the planet itself is far too hot to support life as we know it, the complex organic molecules that likely comprise its atmospheric haze could provide insights into how chemical complexity develops in planetary environments. These processes might be occurring on countless worlds throughout the galaxy, creating a vast cosmic chemistry experiment that we're only now beginning to observe and understand. The implications for astrobiology, while indirect, are nonetheless profound. If planets like Enaiposha can maintain complex atmospheric chemistry for billions of years, then other worlds in more temperate orbits around their stars might host even more sophisticated chemical processes. The diversity of atmospheric conditions that Enaiposha represents suggests that the universe might be far more creative in its approach to planetary development than our limited solar system experience has led us to believe. The discovery also challenges our understanding of planetary migration and formation scenarios. How did Enaiposha acquire its unusual atmospheric composition? Did it form in the outer reaches of its planetary system, where volatile compounds could condense into solid form and then migrate inward, carrying its atmospheric inventory along for the journey? Or did it form closer to its star and somehow manage to capture or generate its thick atmosphere despite the intense stellar radiation? Each possibility has different implications for how common such worlds might be and what conditions are necessary for their development. The red dwarf star that Enaiposha orbits adds another dimension to these questions. Red dwarfs are the most common type of star in our galaxy, comprising roughly 3/4 of all stellar objects. They burn their nuclear fuel so slowly that they can shine for trillions of years, providing potentially stable environments for planetary evolution over timescales that dwarf the current age of the universe. If planets like Enaiposha are common around red dwarf stars, then the galaxy might be populated with billions of super-Venus worlds, each conducting its own unique atmospheric chemistry experiment. The technological triumph of studying Enaiposha also points toward future possibilities for exoplanet research. The methods developed for analysing this world's atmosphere will be refined and applied to other intriguing targets, gradually building a comprehensive picture of atmospheric diversity among planets throughout the galaxy. Future space telescopes, even more powerful than JWST, will be able to study worlds like Enaiposha in even greater detail, potentially revealing seasonal variations, atmospheric dynamics, and chemical processes that we can barely imagine today. The collaborative nature of Enaiposha's study demonstrates how modern astronomy has evolved into a global enterprise that brings together expertise from multiple institutions and countries. The atmospheric modelling, observational techniques, and data analysis methods that revealed this world's secrets required contributions from researchers around the world, each adding their specialised knowledge to solve a puzzle that no single scientist could have tackled alone. The story of Enaiposha also highlights the importance of patience and persistence in scientific discovery. This world was discovered in 2009, but its true nature remained hidden for over a decade until the right combination of technology and techniques became available. The lesson here extends beyond astronomy, reminding us that some of nature's most important secrets require not just clever observations, but also the wisdom to wait for the right tools and approaches to become available. The cultural dimensions of Enaiposha's story add another layer of meaning to its scientific significance. The name itself, drawn from the Ma language and meaning large body of water, connects this distant world to human experience and understanding. While the planet turned out to be quite different from the water world its name suggests, the connection between human language and cosmic discovery reminds us that astronomy is ultimately a human endeavour, driven by curiosity and wonder that transcends cultural and geographical boundaries. The economic and technological implications of studying worlds like Enaiposha extend far beyond pure scientific knowledge. The instruments and techniques developed for exoplanet research often find applications in other fields, from medical imaging to environmental monitoring. The computational methods used to analyse atmospheric spectra from distant worlds can be adapted for studying Earth's own atmospheric chemistry, potentially contributing to our understanding of climate change and atmospheric dynamics here at home. The philosophical implications of Enaiposha's discovery invite us to reconsider our place in the cosmic order. If super-Venus worlds are common throughout the galaxy, and if atmospheric complexity can develop under conditions vastly different from those on Earth, then the universe might be far more diverse and dynamic than our solar system experience suggests. This diversity challenges us to expand our thinking about what's possible in nature, and reminds us that our own world, while precious and unique, represents just one example of how planets can develop and evolve. The educational value of Enaiposha's story extends beyond professional astronomy into classrooms and public understanding of science. This world serves as a perfect example of how scientific knowledge progresses through observation, hypothesis testing, and the willingness to revise our understanding when new evidence emerges. The journey from Waterworld to Super Venus demonstrates the self-correcting nature of scientific inquiry and the importance of remaining open to unexpected discoveries. As we continue to study Enaiposha and other worlds like it, we're building a new understanding of planetary science that encompasses far greater diversity and complexity than we ever imagined possible. Each new atmospheric characterization, each refined model of planetary formation, and each technological advance in observational capability adds another piece to a cosmic puzzle that seems to grow more intricate and beautiful with every discovery. The legacy of Enaiposha will likely extend far into the future as new generations of astronomers build upon the foundation established by its study. The world that once seemed impossibly mysterious has become a touchstone for understanding an entire class of planets, demonstrating that even the most challenging cosmic puzzles can yield their secrets to human curiosity, ingenuity, and persistence. And so our journey through the mysteries of this remarkable world continues, with each new revelation opening fresh avenues for exploration and understanding. Somewhere in the constellation Ophiuchus, Enaiposha continues its eternal dance around its red dwarf star. A cosmic laboratory where the fundamental processes of atmospheric chemistry and planetary evolution play out on scales and under conditions that challenge our imagination and expand our understanding of what's possible in this vast and wonderful universe. The future implications of understanding worlds like Enaiposha extend far beyond the realm of pure scientific curiosity, weaving themselves into the very fabric of how we approach the search for life and habitability throughout our galaxy. While this scorching world with its Venus-like atmosphere certainly won't be hosting any cosmic tea parties anytime soon, its atmospheric complexity offers tantalizing glimpses into processes that might unfold under more temperate conditions elsewhere in the universe. Consider for a moment the remarkable fact that Enaiposha has maintained its intricate atmospheric chemistry for billions of years, despite orbiting so close to its star that it completes a full year in less than 2 Earth days. This persistence suggests that planetary atmospheres might be far more robust and dynamic than we've previously imagined, capable of self-regulation and chemical recycling on timescales that stretch across geological epochs. The organic compounds suspected to exist in Enaiposha's atmospheric haze present particularly intriguing possibilities for understanding how chemical complexity can emerge in extreme environments. These molecules, if they are indeed organic, form through photochemical processes where stellar radiation breaks apart simpler compounds and allows them to recombine in increasingly sophisticated ways. It's rather like having a vast atmospheric chemistry set, where the star provides the energy and the planet's gravity provides the container, allowing countless molecular experiments to unfold continuously in the sky. This atmospheric chemistry laboratory operating above Enaiposha's surface might represent processes occurring on thousands of similar worlds throughout the galaxy. Each of these distant laboratories could be conducting its own unique experiments in molecular complexity, creating compounds and chemical pathways that exist nowhere else in the cosmos. The implications for understanding how complex chemistry develops in planetary environments are staggering, particularly when we consider that some of these worlds might exist in more hospitable temperature ranges where even more sophisticated processes could unfold. The discovery also raises fascinating questions about the role of atmospheric haze in planetary climate regulation. Enaiposha's reflective haze acts like a cosmic parasol, bouncing back much of the incoming stellar radiation and preventing the planet from absorbing as much energy as it otherwise would. This creates a feedback mechanism where the very processes that generate the haze also help control the planet's temperature, suggesting that atmospheric complexity might serve as a natural thermostat for planetary climates. The inefficient heat transport between Enaiposha's day and night sides reveals atmospheric circulation patterns unlike anything we see in our own solar system. This compartmentalization of heat suggests that the planet's thick atmosphere might actually inhibit the kind of global circulation that redistributes energy on worlds like Earth and Venus. Understanding these circulation patterns could provide crucial insights into how atmospheric dynamics work on tidally locked planets, a configuration that might be extremely common throughout the galaxy. The temporal stability of Enaiposha's atmospheric system also challenges our understanding of planetary evolution over cosmic timescales. Red dwarf stars like GJ1214 can shine for trillions of years, providing potentially stable energy sources for atmospheric processes over periods that dwarf the entire history of our universe to date. This longevity means that planets orbiting red dwarfs have vast amounts of time for atmospheric evolution, chemical cycling, and perhaps even the development of increasingly complex molecular systems. The chemical inventory detected in Enaiposha's atmosphere tells us something profound about the building blocks available when this planetary system formed billions of years ago. The presence of heavy elements and complex molecules suggests that the stellar nursery where GJ1214 and its planets were born was rich in the raw materials necessary for atmospheric complexity. This compositional richness might be more common around red dwarf stars than previously assumed, potentially indicating that billions of worlds throughout the galaxy have access to the chemical ingredients necessary for developing sophisticated atmospheric systems. The observational techniques pioneered in studying Enaiposha are already being applied to other intriguing worlds, gradually building a comprehensive picture of atmospheric diversity among planets in the size range between Earth and Neptune. Each new atmospheric characterization adds another data point to our understanding of how these mysterious worlds develop and maintain their unique characteristics over billions of years of evolution. The success with Enaiposha also demonstrates the extraordinary capabilities of the James Webb Space Telescope and points toward even more ambitious future observations. As astronomers refine their techniques and develop new analytical methods, they'll be able to study planetary atmospheres in unprecedented detail, potentially revealing seasonal variations, weather patterns, and chemical processes that we can barely imagine today. The collaborative nature of Enaiposha's study reflects how modern astronomy has evolved into a truly global enterprise, bringing together expertise from institutions around the world to tackle questions that transcend national boundaries and cultural differences. The atmospheric modelling, observational planning, and data analysis required to unlock this world's secrets demanded contributions from researchers across multiple continents, each adding their specialized knowledge to solve a puzzle that no single scientist could have addressed alone. The technological innovations developed for studying Enaiposha's atmosphere will likely find applications far beyond exoplanet research. The data analysis techniques used to extract molecular signatures from faint infrared signals could be adapted for medical diagnostics, environmental monitoring, or industrial quality control. The computational methods developed for atmospheric modelling might contribute to better understanding of climate dynamics here on Earth, potentially helping us address the challenges of climate change and atmospheric pollution. The educational value of Enaiposha's story extends into classrooms around the world, where students can follow the journey from initial discovery through the gradual revelation of this world's true nature. This narrative demonstrates the self-correcting nature of scientific inquiry, showing how new evidence can overturn established assumptions and lead to deeper understanding of natural phenomena. The philosophical implications of discovering worlds like Enaiposha invite us to consider the incredible diversity that might exist throughout the cosmos. If a single planet can harbour such atmospheric complexity under seemingly hostile conditions, what other surprises might await us as we continue exploring the galaxy? The universe appears to be far more creative in its approach to planetary development than our limited solar system experience had suggested. The economic dimensions of exoplanet research, while often overlooked, play crucial roles in enabling discoveries like those made at Enaiposha. The international collaborations, technological developments, and educational programs that make such research possible represent investments in human knowledge that pay dividends across multiple generations and disciplines. As we look toward the future, Enaiposha serves as both inspiration and proof of concept for what's possible when human curiosity meets cutting-edge technology. This world that once seemed impossibly mysterious has yielded many of its secrets to patient observation and clever analysis, reminding us that even the most challenging cosmic puzzles can eventually be solved with the right combination of tools, techniques, and determination. The legacy of studying Enaiposha will likely extend far into the future as new generations of astronomers build upon the foundation established by this remarkable discovery. The methods developed, the questions raised, and the paradigms challenged by this single world will influence exoplanet research for decades to come, shaping how we approach the study of atmospheric diversity throughout the galaxy. The story of Enaiposha also reminds us that scientific discovery often requires patience and persistence, spanning years or even decades. This world was first detected in 2009. But its true nature remained hidden until the right combination of technology and analytical techniques became available more than a decade later. The lesson here extends beyond astronomy, highlighting the importance of long-term investment in basic research and the wisdom of maintaining scientific curiosity even when immediate answers aren't forthcoming. The cultural resonance of Enaiposha's name, drawn from the Ma language and meaning large body of water, creates a poetic connection between human experience and cosmic discovery. While the planet proved to be quite different from the water world its name suggests, this linguistic bridge reminds us that astronomy is ultimately a human endeavour, driven by the same curiosity and wonder that has motivated our species to explore and understand the world around us for thousands of years. The interdisciplinary nature of studying Enaiposha demonstrates how modern scientific research increasingly requires collaboration across traditional academic boundaries. Understanding this world's atmospheric chemistry demanded expertise in astronomy, physics, chemistry, computer science, and atmospheric modelling, showing how the most profound discoveries often emerge at the intersections between different fields of knowledge. As we continue our cosmic journey through the mysteries of this remarkable world, each new piece of information adds depth and richness to our understanding of planetary diversity throughout the universe. Somewhere in the constellation Ophiuchus, Enaiposha continues its eternal orbital dance, a testament to the incredible creativity of nature and the power of human ingenuity to unlock the secrets of even the most distant and enigmatic worlds. The gentle rhythm of discovery continues with each observation and analysis, bringing us closer to understanding not just this single fascinating planet, but the broader principles that govern how worlds form, evolve, and maintain their unique characteristics across the vast expanse of cosmic time and space. The broader implications of studying Enaiposha ripple through our understanding of galactic planetary populations like gentle waves across a cosmic pond, each revelation creating new questions that challenge our assumptions about how common or rare different types of worlds might be throughout the Milky Way. When we consider that sub-Neptune planets like Enaiposha represent the most numerous type of world discovered by our planet-hunting missions, yet remain completely absent from our own solar system, we begin to appreciate just how unusual our cosmic neighbourhood might actually be. This realization is both humbling and slightly unsettling, rather like discovering that the architectural style of your hometown is virtually unknown in the rest of the world. For centuries, we've used our solar system as the template for understanding planetary formation and evolution, assuming that the progression from small rocky worlds to massive gas giants represents the natural order of things. But Enaiposha and its countless cousins throughout the galaxy suggest that nature has been far more creative in its approach to world building than we ever imagined. The abundance of these intermediate-sized worlds raises profound questions about the processes that govern planetary formation in stellar nurseries throughout the galaxy. If planets in the size range between Earth and Neptune are so common elsewhere, why didn't any form in our own system? Was there something unique about the conditions in our particular stellar nursery 4.5 billion years ago that prevented such worlds from developing, or did they form and subsequently migrate away or get ejected from the system entirely? These questions touch on some of the deepest mysteries in planetary science, because understanding why certain types of worlds are common or rare requires us to reconstruct events that occurred billions of years ago under conditions we can never directly observe. It's rather like trying to understand why certain architectural styles emerged in particular regions by examining only the buildings that survive today, without being able to witness the historical, cultural, and environmental factors that influenced their original construction. The discovery of atmospheric complexity on Enaiposha also suggests that the galaxy might be populated with countless worlds conducting their own unique atmospheric chemistry experiments. Each of these distant laboratories operates under different conditions of temperature, pressure, stellar radiation, and chemical composition, potentially creating molecular diversity that extends far beyond anything we see in our own solar system. Imagine, if you will, a vast cosmic library where each planet represents a different book, written in the language of atmospheric chemistry and telling the story of billions of years of molecular evolution. Enaiposha represents just one volume in this incredible collection, but already its pages reveal chemical processes and atmospheric dynamics that we never knew were possible. How many other fascinating stories await discovery in the atmospheres of distant worlds orbiting stars throughout our galactic neighborhood? The temporal aspects of these atmospheric evolution stories add another layer of wonder to the cosmic narrative. Red dwarf stars like the one that Enaiposha orbits can shine steadily for trillions of years, providing stable energy sources for atmospheric processes over timescales that stretch far beyond the current age of the universe. This longevity means that planets around such stars have essentially unlimited time for atmospheric evolution, chemical cycling, and the development of increasingly sophisticated molecular systems. The patience of cosmic timescales is difficult for human minds to truly grasp. While we measure our lives in decades and our civilizations in millennia, planets like Enaiposha have been conducting their atmospheric chemistry experiments for billions of years and will likely continue doing so for trillions more. It's rather like comparing the brief flicker of a camera flash to the steady glow of a lighthouse beam that shines across geological epochs. This temporal perspective also highlights the remarkable stability that some planetary atmospheric systems can achieve. Despite orbiting so close to its star that it experiences extreme temperature variations and intense stellar radiation, Enaiposha has maintained its complex atmospheric chemistry for eons. This persistence suggests that planetary atmospheres might be far more resilient and self-regulating than we've previously assumed, capable of maintaining chemical complexity through feedback mechanisms and recycling processes that operate on truly astronomical timescales. The technological achievements that made studying Enaiposha possible also point toward exciting possibilities for future exoplanet research. The methods developed for analyzing this world's atmospheric composition will be refined and applied to other intriguing targets, gradually building a comprehensive picture of atmospheric diversity among planets throughout the galaxy. Each successful observation adds another piece to the puzzle of how planets develop and maintain their unique characteristics over billions of years of evolution. Future space telescopes, even more powerful than the James Webb Space Telescope, will be able to study worlds like Enaiposha in even greater detail, potentially revealing seasonal variations, weather patterns, and dynamic atmospheric processes that we can barely imagine today. These next-generation instruments might even be capable of detecting atmospheric biosignatures on more temperate worlds, opening entirely new chapters in our search for life beyond Earth. The collaborative nature of modern exoplanet research, exemplified by the international team that studied Enaiposha, demonstrates how astronomical discovery has become a truly global enterprise. The atmospheric modeling, observational techniques, and data analysis methods required to unlock this world's secrets demanded contributions from researchers around the world, each adding their specialized expertise to solve puzzles that transcend national boundaries and cultural differences. This collaborative approach reflects a broader trend in scientific research, where the most profound discoveries increasingly emerge from interdisciplinary teams that bring together diverse perspectives and complementary skills. Understanding Enaiposha's atmospheric chemistry required expertise in astronomy, physics, chemistry, computer science, and atmospheric modeling, showing how modern science flourishes at the intersections between traditional academic disciplines. The educational dimensions of Enaiposha's story extend far beyond professional astronomy, reaching into classrooms and public understanding of science around the world. This world serves as a perfect example of how scientific knowledge progresses through careful observation, hypothesis testing, and the willingness to revise our understanding when new evidence emerges. The journey from initial discovery to atmospheric characterization demonstrates the self-correcting nature of scientific inquiry and the importance of maintaining curiosity and open-mindedness in the face of unexpected results. The economic implications of exoplanet research, while often overlooked in popular discussions, play crucial roles in enabling discoveries like those made at Enaiposha. The international collaborations, technological developments, and educational programs that make such research possible represent investments in human knowledge that generate returns across multiple generations and scientific disciplines. The instruments and analytical methods developed for studying distant worlds often find applications in fields ranging from medical diagnostics to environmental monitoring, demonstrating how basic research in astronomy can contribute to solving practical problems here on Earth. The philosophical resonance of discovering worlds like Enaiposha invites us to contemplate our place in the cosmic order with renewed wonder and humility. If a single planet can harbour such atmospheric complexity under seemingly extreme conditions, what other surprises might await us as we continue exploring the galaxy? The universe appears to be far more creative and diverse in its approach to planetary development than our limited solar system experience had suggested. This diversity challenges us to expand our thinking about what's possible in nature and reminds us that our own world, while precious and unique, represents just one example of how planets can develop and evolve. The chemical processes occurring in Enaiposha's atmosphere might be replicated on countless other worlds throughout the galaxy, each conducting its own unique experiments in molecular complexity and atmospheric evolution. The story of Enaiposha also serves as a reminder of the importance of patience and persistence in scientific discovery. This world was first detected in 2009, but its true nature remained hidden for over a decade until the right combination of technology and analytical techniques became available. The lesson here extends beyond astronomy, highlighting the value of long-term investment in basic research and the wisdom of maintaining scientific curiosity even when immediate answers aren't forthcoming. The cultural dimensions of Enaiposha's discovery add human meaning to cosmic exploration, connecting the vast scales of astronomical research to the intimate experience of wonder and curiosity that drives our species to seek understanding. The name Enaiposha itself, drawn from the Ma language and meaning large body of water, creates a poetic bridge between human experience and cosmic discovery, reminding us that astronomy is ultimately a human endeavour motivated by the same sense of wonder that has inspired exploration and discovery throughout our history. As we continue to study this remarkable world and others like it, we're participating in one of humanity's greatest adventures, the gradual unveiling of cosmic diversity and the patient construction of knowledge that spans generations and cultures. Each new observation, each refined model, and each technological advance adds another thread to the tapestry of understanding that connects us to the broader universe and reveals our place within the grand cosmic story. The gentle rhythm of discovery continues, with each piece of new information adding depth and richness to our appreciation of planetary diversity throughout the cosmos. Somewhere in the constellation Ophiuchus, Enaiposha maintains its eternal orbital dance, a testament to nature's creativity and a reminder that the universe still holds countless secrets waiting to be discovered by future generations of cosmic explorers. And so our journey through the mysteries of this extraordinary world draws us ever deeper into questions that touch the very foundations of planetary science, atmospheric chemistry, and our understanding of how diverse and wonderful the cosmos can be. The story of Enaiposha reminds us that every distant point of light in the night sky might harbour its own unique collection of secrets, waiting patiently for the right combination of human curiosity, technological capability, and collaborative spirit to reveal the wonders hidden within. The legacy of Enaiposha extends far beyond the boundaries of a single discovery, weaving itself into the very fabric of how we approach the fundamental questions that have captivated humanity since we first gazed upward at the star-scattered darkness and wondered what secrets might be hidden in those distant points of light. This remarkable world has become a bridge between what we thought we knew about planetary formation and the vast unexplored territories of cosmic possibility that stretch out before us like an infinite ocean of mystery. As we stand at this crossroads of understanding, Enaiposha serves as both guide and inspiration for the next phase of our cosmic exploration. The atmospheric complexity revealed in its thick, hazy envelope suggests that the universe operates according to principles far more nuanced and creative than our terrestrial experience had prepared us to imagine. Each molecule of carbon dioxide, each trace of water vapor, Each organic compound suspended in that distant sky tells a story of processes that have been unfolding for billions of years in ways that challenge our most sophisticated theoretical models. The methodological breakthroughs achieved in studying this world have opened new pathways for investigating atmospheric diversity throughout the galaxy. Future observations will build upon the foundation established by these pioneering measurements, gradually constructing a comprehensive understanding of how planetary atmospheres develop and maintain their unique characteristics across the vast range of conditions that exist in stellar systems throughout our cosmic neighborhood. The technological symphony that enabled these discoveries represents one of humanity's greatest achievements in precision measurement and data analysis. The James Webb Space Telescope, with its golden mirror and exquisitely sensitive instruments, has proven capable of detecting atmospheric signatures so subtle that finding them required statistical techniques that push the very boundaries of what's possible with current computational methods. These capabilities promise even more remarkable discoveries as astronomers turn their attention to other enigmatic worlds orbiting distant stars. The interdisciplinary collaboration that made Enaiposha's atmospheric characterization possible demonstrates how modern scientific discovery increasingly requires the synthesis of expertise from multiple fields of knowledge. Atmospheric modelers, observational astronomers, data analysts, and theoretical physicists have worked together to decode signals so faint that they might easily have been lost in the cosmic background noise, showing how the most profound insights often emerge when diverse perspectives combine to tackle seemingly impossible challenges. The philosophical implications of discovering atmospheric complexity on a world so different from anything in our own solar system invite us to reconsider our assumptions about the prevalence of chemical sophistication throughout the universe. If molecular diversity can flourish under the extreme conditions that exist on Enaiposha, then the cosmos might be populated with countless worlds where chemistry operates according to principles we've barely begun to explore. The temporal dimensions of this story add layers of wonder that stretch across geological epochs and into futures so distant they challenge human comprehension. Red dwarf stars, like the one that illuminates Enaiposha's perpetual day, can shine steadily for trillions of years, providing stable energy sources for atmospheric evolution over timescales that dwarf the entire history of our universe to date. This longevity means that the chemical processes we observe today represent just a single moment in an evolutionary journey that could continue for eons beyond our ability to imagine. The educational resonance of Enaiposha's discovery extends into classrooms and public understanding around the world, where students can follow the progression from initial detection through the gradual revelation of atmospheric secrets that transformed our understanding of what's possible on distant worlds. This narrative demonstrates the iterative nature of scientific progress, showing how patient observation and careful analysis can eventually unlock even the most stubborn cosmic mysteries. The economic dimensions of exoplanet research, while often invisible to public attention, play crucial roles in enabling the kind of long-term observational campaigns that made studying Enaiposha's atmosphere possible. The international collaborations, technological developments, and educational programs that support such research represent investments in human knowledge that generate returns across multiple generations and scientific disciplines. The cultural significance of connecting human language to cosmic discovery through names like Enaiposha creates bridges between the vast scales of astronomical research and the intimate experience of wonder that motivates our species to seek understanding. These linguistic connections remind us that astronomy remains fundamentally a human endeavour, driven by curiosity and imagination that transcend cultural boundaries and geographical distances. As we look toward the future, Enaiposha stands as both achievement and inspiration for the next phase of our cosmic exploration. The world that once seemed impossibly mysterious has yielded many of its secrets to human ingenuity and technological prowess, demonstrating that even the most challenging puzzles in the universe can eventually be solved through patience, precision, and collaborative effort. The story continues to unfold with each new analysis of the data collected by the James Webb Space Telescope, potentially revealing additional details about atmospheric dynamics, seasonal variations, or chemical processes that we haven't yet discovered. Future observations may uncover new aspects of this world's character, adding fresh chapters to a narrative that has already transformed our understanding of planetary diversity. The techniques pioneered in studying Enaiposha are already being applied to other intriguing worlds, gradually building a comprehensive picture of atmospheric complexity among planets throughout our galactic neighborhood. Each successful characterization adds another piece to the puzzle of how worlds develop their unique personalities over billions of years of evolution under conditions that span the full range of cosmic possibility. The collaborative networks established through this research continue to grow and evolve, bringing together expertise from institutions around the world to tackle questions that transcend national boundaries and cultural differences. These partnerships demonstrate how scientific discovery flourishes when diverse perspectives combine to address challenges that no single researcher or institution could solve alone. The technological innovations developed for atmospheric spectroscopy continue to find applications beyond exoplanet research, contributing to advances in fields ranging from environmental monitoring to medical diagnostics. The computational methods refined for analyzing faint signals from distant worlds help scientists extract meaningful information from complex datasets across many different disciplines. And so our gentle journey through the mysteries of this remarkable world draws toward its close. But the questions it has raised and the methods it has inspired will continue to shape astronomical research for generations to come. Somewhere in the constellation Ophiuchus, 48 light-years from our own pale blue dot, Enaiposha continues its eternal dance around its red dwarf star, a cosmic laboratory where the fundamental processes of atmospheric chemistry unfold, according to principles we're only beginning to understand. The universe, it seems, still holds countless secrets waiting to be discovered by future generations of cosmic explorers, armed with ever more sophisticated tools and guided by the same sense of wonder that has driven human curiosity since our ancestors first looked up at the night sky and wondered what marvels might be hidden among those distant points of light. As you drift gently toward your own dreams tonight, perhaps you'll carry with you the image of that distant world, shrouded in its mysterious haze, conducting its billion-year experiments in atmospheric chemistry beneath the steady glow of its ancient red star. And maybe, just maybe, you'll find comfort in knowing that the universe continues to surprise us with its creativity, reminding us that no matter how much we think we understand about the cosmos, there are always new wonders waiting to be discovered just beyond the edge of our current knowledge. Sleep well, fellow traveller, and may your dreams be filled with distant worlds and the gentle mysteries they whisper across the vast expanses of space and time. Expanses of space and time.